Good morning, everyone. If you open your notebook, the table of contents, put this title, Maximizing Motor Power and Constant Voltage, and then turn to the next blank page in your notebook, put this title on the top, box it in, put today's date next to it. If you don't have your notebook with you, you can always put on another piece of paper and then insert it or transpose it to your notebook later on. Okay, so here we go. What we're going to look at today, basically, kind of think of it as the windows in your car, if you have power windows, right? How do engineers know what size motor to use, what voltage to use, what gears to use to make sure the motor can lift the window safely, well, to open and close your window safely, and that we didn't do it too fast, didn't too slow, or to make sure that the motor can lift the window at all, because what would be worse than not being able to open or close your window. So the first thing we're going to look at, when a motor is loaded with no torque, it spins at no load speed, or omega O. So go ahead and write that down, omega O, and that is equal to no load speed. Then when a motor is loaded with the stall torque, and that's tau, the Greek letter tau, so stall torque or more, the motor will stop. So go and write that down at the bottom. Torque stall equals stall torque, or tau stall. Okay. Here we have a graph. You can draw it if you'd like to, you don't have to. But we see on the y-axis over here as a speed, and then the x-axis is our torque, omega O. We see the no load speed. Down over here on the end of the line, we see the stall torque, and of course in between is going to be our half speed. Going down this equation here, we're going to come back to it in a minute, but it's good to have your notes. So we have angular speed, or omega, is the negative no load speed divided by stall torque times torque plus no load speed. So optional slide for the genius. Speed versus torque depends on voltage. So we have 7 volts, 5 volts, and 3 volts. And remember, in electrical circuits, voltage is our force or our pusher. So obviously the more voltage you have here, the more force you have. So 7 volts is going to have more output and speed and torque than 5 volts. And 5 volts will have more output, speed, and torque wise than 3 volts. And see motor speed here of 120, 90, and then 60. On those three at 7, 5, and 3 volts. Go and write this equation down. P is tau times omega. So you have power is equal to torque times angular speed. And we see this graph again. And so we look at our 2 points, the no load speed, and it says no power y. Okay, so think about that for a second. And then down here it says stall torque, no power y. Okay, well, think about it. If we're on this axis, it's the y, but our x is 0, so anything times 0 is going to be 0, so that's why we have no power. Over here, same thing. We're on the x-axis, but our y is 0, so therefore anything times 0 is 0, so we have no power there again. This is maximum power, and that is half the stall torque, and we're going to figure out why that is in a second. So this is maximum power at half stall torque. If you want to go and write down this title up here, that's important. Maximum power at half stall torque. Okay? And remember, you can pause the video at any time, of course, to take more notes if you'd like. And so then we're back to this equation again. I told you to write down a minute ago. So we're going to look at that equation a little bit further. So why half stall torque? So there's the equation that we just saw, linear equation from last slide. We multiply both sides by torque. Part on the left is power. So if we take torque on both sides, remember, omega times torque is power. That's how they got the P over here. And so then we took this part of the equation, put it in brackets, and then put torque next to it again, like it said in the directions, multiply both sides by torque. And so we do that, and we distribute the torque. Then we have the negative no load speed divided by stall torque times torque squared now, and then that's plus the no load speed times torque. So we distribute that torque across here. And when you do that, that is a down-facing parabola, like this. And so if we graph that, then, and this is the equation up here, so that's the max power, is going to be no load here with 0, 0. Then we climb up this, that's our half stall torque. And then, of course, we go back down, we go any further, and that becomes our stall. So no load on one end, stall on the other. The middle, the peak of our parabola would be our half stall torque. So you want to go ahead and write down this equation. The power equation up here, that's max power equation right there. Okay? So now to apply this to an actual gear ratio. So step one, the motor is stalled. What is the stalled torque? So we see a force of 1.4 pounds on this little sensor over here. We see a distance, because here's the motor, there's the shaft, and they have this VEX piece on there. Its length is 3 inches. That's our distance. So what torque will the motor deliver maximum power? So in the first part of here, step one, look at the stalled torque. So it's force times distance. We have 3 inches times 1.4 pounds. So 4.2 inch-pounds, or pound-inches. For number 2, looking at what torque will the motor deliver maximum power. If we do max power, that's the half stalled torque. We do 1/2 of our stalled torque up here, and then we get 2.1 pound-inches. So we took our stalled torque, half of that, and that is our max power. Step 3, the same motor as in the last slide is being used to power a winch with a drum of radius 2 inches. So we see that radius right here from the center of the shaft to the outside of the wheel or drum. And it lifts. Right here we see a weight hanging off that is 0.2 pounds. What torque is the motor applying? Well, we do that once again here, force times distance. This is the torque out though. And then it's 2 inches for the drum radius times 0.2 pounds. We get 0.4 pound-inches. I want to go back real quick for a second and verify that this is the stall torque and this is the max power. Right now, here on step 3, we solve for the torque out, just to clarify. So step 4, instead of direct drive, what gear ratio would make the motor deliver maximum power? So this is where the gears come in. So they have torque out of 0.4 inch-pounds we solved for. Torque in would be the 2.1 inch-pounds that we solved before that. And so we have a gear ratio of 0.19. In our VEX kits, the 2 gears that give us the closest to 0.9 that we can get, or 0.19, I'm sorry, is 12 teeth over 60 teeth. Those are the 2 sizes that will come closest to that ratio. So now they've changed the picture. You see that they put the smaller 12 teeth on the shaft with the drum, and then they put the larger 60 tooth gear on the shaft, on the motor shaft. So that's the input. So 60 is the input, and then 12 is the output. That 12 is on the same axle as the drum that lifts the weight. So now the winch is geared, so the motor is delivering half its stalled torque for maximum power. So bicycle gears, can you explain why changing gears on a bike helps a person win a race that goes up and down hills? So there's 2 things to look at when we look at bicycles. One is the input sprocket, where your feet pedal, obviously, and the one is the output sprocket on the actual wheel itself. So if you're ever going uphill, you want to go to a smaller sprocket that was easier for you to pedal, because that way you pedal more revolutions a second or minute, but you put in less effort force. Trying to go uphill makes it easier for you. Same thing over here, well, opposite actually. When you want to go uphill, you go to a larger sprocket. That way it's easier, makes it easier for you to pedal. On level ground, then sometimes you have 3 sprockets up here. You can use middle sprocket level ground, and then just use these as kind of small change in gear ratio, and then that kind of makes your ride a little bit simpler. If you're going downhill, believe it or not, professional bikers still pedal to gain momentum, even going downhill, where most of us would coast to take a break or a rest. But they would go to a larger gear here. They put in lots of force, but since they're already going fast downhill, all they're doing is adding to speed. They don't have to pedal as fast, but they do pedal harder. And then back here, they would go to a smaller gear, or smaller sprocket, I'm sorry, and that would also help add to the momentum as you're going downhill. So professional bicyclers are always pedaling, level ground, uphill, downhill, always pedaling to always gain momentum and gain speed. Okay, and that's it. Like I said, this activity's really dangerous, and it's complicated, so I decided to go ahead and skip it, but it's still a good concept to go over. So we're done with the notes now. See if you want to go ahead and cross the page out. It's on the line, it's on the bottom of the page, and date it, and then have witness sign date. And if you don't have witness right now by you, you can get a witness later in class. And everyone have a good day. We'll talk to you later. Thank you. Bye-bye.